hang on here. Breakthrough initiatives were founded in 2015 by Silicon Valley entrepreneur and investor Yuri Milner, pictured there on the left. They were founded with Stephen Hawking, who was our science advisor while he was still alive. And they seek to kind of answer some of the most fundamental questions about kind of life in the universe. And these are the three major questions. Is there other life in the universe? Is it intelligent? And finally, can we visit it? So to answer the first question, we have an initiative called Breakthrough Watch, which is a sort of traditional-ish astronomy program seeking to characterize exoplanets around the nearest stars, particularly focused on Alpha Centauri. We've had instruments on the VLT, which are trying to directly image exoplanets around Alpha Centauri in the infrared, using a coronagraph and a number of other novel techniques. We are currently building a small satellite mission, well, a 6U astrometry mission to try to determine the mass of a potential planet around in the Alpha Centauri system. And so that's kind of to try and understand what our nearest sort of stellar neighborhood is like. We're very lucky that Alpha Centauri, while a binary system, is actually a couple of sun-like stars, so it is possible that there is an Earth analog there. Breakthrough Listen is trying to answer the second question about whether life might be intelligent elsewhere in the universe. It is a revived SETI search. We are monitoring the nearest 1,000 stars with time on some of the biggest telescopes, radio telescopes in the world, and have started also moving into the optical wavelength. As our own technology develops, we realize that increasingly alien civilizations may communicate using different wavelengths. This is run out of UC Berkeley, and we have a team of about 14 scientists working full time on it. And then finally, the project that I work on, Breakthrough Starshot, is meant to answer that third question. You know, if we find a habitable planet, if we think that there's life somewhere nearby, is there any way that we could reach it physically? So could we travel between the stars, and can we do it in a sort of human time frame rather than the 70,000 years that it's going to take the voyagers to reach our nearest stars? Starshot objectives, therefore, are to send the spacecraft to a star with a planet in the habitable zone within 5 parsecs, to take science data and to send that data back to Earth, to launch within 30 years and to go fast. So, and by fast we mean about 1/5 of the speed of light, which would cover that distance in about 20 years. Now, you probably are all familiar with the rocket equation and what we call the sort of tyranny of the rocket equation. That the faster you want to go, the more mass you have to take with you in fuel, and that rapidly becomes an impossible prospect. So the final velocities that we're looking at, sort of near relativistic speeds, you would need a specific impulse of a million. Now, to put that in context, regular hydrazine rockets get about 200. Shuttle got about 250. So there is virtually no way that traditional rocketry is going to get us to the velocities we need. It turns out actually that you would need to take the mass of about all the stars in the galaxy in fuel to get to those kinds of velocities. So there are several strategies to overcome this problem. You can either obviously raise your power, which is what I described, or reduce your weight. And different vehicles have used different kind of different versions of this. So airplanes and cars obviously keep their power and their propellant on board. Regular spacecraft, the power is external, but they have propellant on board. And for our approach, we are trying to leave both the power and the propellant behind, using a laser-driven light sail approach. So we have a concept for an enormous, several kilometer in diameter laser that we call the photon engine, because it's an engine made of light essentially, and then an ultra-thin, ultra-lightweight sail membrane that would be accelerated using photon pressure. This is an artist's concept of what they might look like, riddled with holes from the interplanetary medium, or the interstellar medium. This is a sort of diagram of what the whole mission looks like. You'd have a mothership that would deploy these sailcraft. They would be accelerated over about 10 minutes by this 100 gigawatt laser, and would then it would then cruise for 20 years before sending science data back to Earth. But it turns out even 100 gigawatts isn't enough for a conventional spacecraft. it wouldn't give us the velocities that we need if we were sending even a CubeSat. And so our one of the main things about our solution to go fast is that we have to take the lowest possible mass, which means reducing the payload to essentially a single chip. Now, there are trends in electronics and photonics that actually look very promising and we believe are going to help us get there. You're all obviously familiar with Moore's law, and this logarithmic plot shows just how much cheaper computation has become over the last 100 years, and continues to get smaller and cheaper year by year. So this is one of the an iteration of a ChipSat produced by Zach Manchester at Cornell and launched by NASA, Cornell, and Stanford, I think early last year. And I think Zach may have given the presentation on this last year. So this is a simple transmitter, kind of like a Sputnik that they launched just to prove that we could actually track and communicate with these tiny spacecraft. Our next iteration will be much smaller than that even, but this mock-up kind of shows that you could fit all of the components that we might need on a functioning spacecraft into an extremely small surface area and mass. And now, to put this in context, it's not that much smaller than the chip in an Apple Watch, and we all know that that's a very functional piece of computation equipment, right? So in the context of what's going on in consumer electronics, this doesn't actually seem that outlandish to us. Again, this slide illustrates just how much we've progressed in 20 years, going from sort of 84 grams. We can now fit all of those components theoretically into about a third of a gram. This is a crude representation of what you might look like, and it's sort of the first thing that many people think of is that you would just attach your spacecraft, this little chip, to a sail. But in fact, partly because of the 60,000 Gs that the spacecraft will experience during acceleration, you don't really want differential mass across the thing. You want the mass density to be pretty much uniform, and so it's likely that we will use some slightly more novel or have to leverage sort of novel technology going forward. And so while today we're looking at these tiny chips, we may end up going towards sort of these flexible laminates, or even utilizing the developments that are being made in photonic chips, which are computationally much less power hungry than classic electronic chips. And the spacecraft may actually be distributed across the entire sail rather than being a sort of separate payload component. So, in the light of that, we're about to release our interstellar communications RFP. So the Interstellar Communications Challenge is the third leg of our sort of technology development program. The first being the giant laser, the phased array photon engine. The second is a materials challenge, materials and stability really, to try and develop the ultra high, the ultra reflective, extremely lightweight, sturdy sail membrane. And then this last one is really what I think of as our payload challenge, although we're focused on communications because that seems like the biggest problem in this, is that with extremely low power and very small mass and size, how do you transmit useful data over 4 light years across the interstellar medium with interference from the star that you're right in the vicinity of? And for everyone here, it might be that the second one is the most interesting, the onboard transmitter itself. So here we're interested in subsystem components that can meet the size, weight, and power requirements of the transmitter, but are also interested in various other components that can do sensing and the other important functioning parts of any kind of spacecraft, but on this incredibly small scale. So hopefully we'll be this is $1 to $2 million in basic research grants, probably in the $100,000 to $150,000 range for a year, and I hope we'll be launching this towards the end of the year. So stay tuned or send me an email if you're interested. Now, before we go on, I just want to say that I don't necessarily think that chipsats are a sort of logical conclusion to the miniaturization of spacecraft. I think there are useful things that can be done at various various sizes and masses, and that you shouldn't necessarily think that that the logical conclusion of the small sat revolution is to finally make our way down to chipsats. And this set of slides is borrowed from Professor Hunter Adams at Cornell, in which he sort of outlines his view of where chipsats really are useful and where they might not be. So rather than being, as he says, an incremental improvement upon conventional spacecraft, they're a sort of fundamentally different type of spacecraft. And he uses, I think, a very neat analogy from evolutionary biology about R and K selection. So here, if your goal is to make sure that enough offspring survive to reproduce to the next generation, there are two different approaches. There's K selection, which is used by most large mammals like humans, and many birds and other animals like that, where you produce relatively few offspring, and then you spend a lot of time trying to make sure that they survive. And it's well suited to stable environments where long lifespans and low mortality rates allow you to put that kind of energy into keeping your offspring alive. Our selection, on the other hand, applies to a different set of animals like rodents and insects and octopuses. And here you produce large quantities of offspring, and you basically spend no effort at all. An octopus will produce something like 500,000 eggs, just a tiny fraction of which will survive. And that's much better suited for unstable environments and where things have shorter lifespans and higher mortality rates. And so basically, if there's a high probability that your offspring won't survive, you produce as many of them as possible. Now, if you, I think quite cleverly, he proposes that the spacecraft, this paradigm kind of applies to spacecraft as well. So in the case selection, we have what we've always done for regular spacecraft. So you spend all the engineering and money you can on making sure that your one exquisite satellite does not fail. And it's extremely expensive and extremely time consuming. And our selection would be the chipsat approach, where you now can say, produce almost an infinite number of these. They're perfectly replaceable, extremely cheap. And you can overcome the high probability of spacecraft failure just by producing and launching many more of them. And this, of course, is well suited for unstable environments, and where if a system failure might disable an entire huge satellite, it's much less of a problem if you lose a third of your 1,000 or 10,000 microsatellites. Historically, of course, we could only do K selection, but the advances in computation and miniaturization have allowed us to move into this R selection world potentially for spacecraft. Now, as I said, if you think about when you want to use chipsats, you want to do it when you want to produce large quantities of spacecraft and devote as little as time as possible to making sure that they're perfect. So it's good, obviously, for hobbyists, students, people who are looking for a low barrier to entry. But it's also particularly well suited for unstable environments. So places where it would be risky to send a $100 million spacecraft. There are other obvious benefits. Potentially having distributed measurements gives you access to highest spatial resolution. And planetary surfaces and very low orbit science missions can be accessed easily by littering atmospheres and planetary surfaces with chipsats, which could take measurements across a large large surface area. There are also ideas of using them for health monitoring, and of course you could do large artificial aperture searches for gravity waves and things like that. So there are interesting kind of potential uses of these. Now, Mason Peck, who was the former NASA chief technologist and then a professor at Cornell, and sort of the father of the chipsat concept, I guess, points out that that subsystem technology is basically already available. We don't have to push. This is one of the great things about this. We don't really have to push for push microfabrication boundaries. That's happening already in a whole bunch of consumer industries. What we really need, I would posit, is we need testing and experimentation. We haven't, I don't think, found the killer app yet, and we need just to get more and more people access to this technology and to flying it. Of course, this is where it gets difficult because there are major regulatory issues when it comes to chipsets. The FCC considers them too small to track, even if this is untrue, because you can stick an antenna on them, which makes them light up to any kind of tracker. But the FCC is not exactly a home to a suite of technically capable people. It is America's communications regulatory body that has taken on this role of regulating space debris in a very strange bit of a regulatory creep. So they haven't even really figured out how to deal with hundreds of small satellites being launched every year. They're much more used to sort of a dozen large satellites. And so how they're ever going to get their head around tracking hundreds or thousands of chipsats is a really worrying problem. They've basically taken an adversarial approach. It's hard. I think it's harmed the CubeSat revolution, and it certainly has the potential to kill the sort of nascent chipsat revolution. The decisions are arbitrary. You basically have to make your case to a particular person, and that who may change. It's really a mess. So how do we get around this problem? For now, sometimes you can do missions directly with NASA who don't have to apply with the FCC. That's how those sprites got launched. But we have an exciting opportunity coming up that might be a great showcase of what chipsats can do. I don't know if some of you saw this article in the New York Times a couple of weeks ago about a theory that there may be signs of life on Venus in the clouds. This was published based on a paper published by Professor 𝗖cie and a colleague at Harvard, who have taken 2 different readings that indicate that there's phosphine in the upper atmosphere of Venus. Now, phosphine is a gas that can be produced, in the enormous pressures of the atmosphere of Jupiter, for instance. But at least according to our models, a much smaller planet like Venus shouldn't really be able to produce this gas without some sort of biological process. So we have given them a $300,000 grant to look into this further and to come up with a mission concept. So we've just started this work. We're looking for, it's a sort of hypothesis-driven mission. We're going to try to understand what we can do to sample the atmosphere and to detect signs of life. And we'd like to do it like everything. We'd like to do it innovatively and cheaply. So there are 3 different sort of types of missions we can do: the large-scale, classic NASA-style missions, a medium-scale one where we might deploy something in a balloon in the atmosphere for some amount of time, or even a small one where we send a drop package with potentially sort of hundreds of chipsats that might be deployed and be able to take in-situ measurements as they descend through the atmosphere. Some people have actually already looked at this. This is a paper by 𝗖cie viņš, Dan Fries and Chris Welch, which looked into the potential of using chipsats on Venus. And even an unmodified chipsat, it turns out, would have a 90-second hang time in the temperate zones in Venus, which could be improved. So even that would give us really interesting and fascinating data on in an extremely unstable environment. So the ideal sort of place to use chipsats. Here is a list of potential payloads. We can do pressure detections easily, temperature detections. You can even now do single chemical detections on a chip. There are hardware accessories that you can attach to your smartphone that can detect for specific chemicals. So I think the possibilities here are pretty endless and exciting. And I encourage anyone here who's interested in this kind of miniaturization to reach out or to think about what kinds of sensors we could use to do a really exciting mission in Venus. So I think that's my time, and thanks very much for listening.